Hi everybody, it's Giacomo Lanciano here. I'm a PhD student in data science, currently working at the Retis lab of Scuola Superiore di Sant'Anna in Pisa, one of the major Italian schools of advanced studies. The article I'm going to present is a joint work between Scuola Sant'Anna and the Vodafone Group. Specifically, this article describes our evaluation of different approaches to time series forecasting in the context of an NFV infrastructure that is already being employed by Vodafone throughout its NFV data center to support their monitoring and reporting activities. During the last years, network services providers have been progressively changing their operational models to adhere to the network function virtualization paradigm. Such approach is particularly suitable to tackle the increasingly demanding requirements and complex scenarios of the future internet. Indeed, by means of modern technologies like cloud computing, it has been possible to replace the traditional network functions deployments based on specialized physical appliances, typically sized for the peak hour and very costly to maintain, with more flexible and robust infrastructures. VNF are typically implemented as a distributed software application that can be deployed on a private cloud managed by a network operator, enabling elastic and resilient services that can be easily reconfigured according to the requirements of highly dynamic workloads. The choice of private cloud infrastructures, beside obvious possible privacy issues, is also corroborated by latency-related concerns. Indeed, such service chains are highly delay sensitive, so it is unpractical to rely on public cloud providers whose resources are usually shared among multiple tenants and not necessarily deployed such that the network operator's service level agreements can be met. For these reasons, it is crucial to effectively monitor the status of the data center through an efficient distributed monitoring infrastructure that continuously gathers system-level metrics from all the different levels of the architectures. For instance, physical host metrics, virtual machine metrics, application-level key performance indicators, event logs, and so on. Such data usually drives the decisions of human operators. For instance, in terms of which action must be taken to restore the expected conditions of the system after an outage has occurred, or how the available components should be reconfigured to prevent possible SLA violation in case of an unexpected increase in the workload. The goal of this work is to address the problem of forecasting NFV operation metrics, registered both at infrastructure level and service level metrics. In particular, we investigate on the performance of a number of time series forecasting techniques and provide insights on how they can support the decisions of NFV operation teams. Indeed, such techniques can provide an accurate snapshot of the system dynamics in the future, and this kind of information is very useful to operation teams when they need to carry out their daily tasks, like capacity planning, for instance. Nowadays, deep learning has been gaining a lot of momentum, both in industry and academia. The techniques coming from this field are usually very good at dealing with this type of tasks, as they are designed to discover possibly very complex non-linear relations in the input data. In this work, we described some neural architectures for time series forecasting that are being used at Vodafone in their NFV data centers and compared them to classic forecasting techniques to highlight the kind of performance improvement that one can achieve by employing them in production. This figure shows how forecasting capabilities enhance Vodafone NFV operations. The MVI time series produced by each component of the infrastructure are ingested by the VMware Virtualized Operation Manager, VirOps, and the monitoring subsystems of the individual VNFs. The analytics engine sits in front of these monitoring components and computes NVI forecasts. Such outputs are used in a semi-automated decision-making process, where humans consume them to get insights and possibly uncover early symptoms of system outages. The acquired knowledge provides decision makers with actionable feedbacks that may trigger capacity planning and infrastructure management actions. The data provided by Vodafone for this work consists of a set of relevant metrics, each one coming in the form of a time series that describes the evolution of a specific MVI metric. Dealing with time series, especially in multivariate settings, is an inherently complex problem. To be effective, the model that implements the analytics engine must take into account the dynamic and sequential nature of the information. Furthermore, possible high variance in the data poses an additional challenge. In this work, we considered four main types of approaches to time series forecasting, coming both from the classical literature and the deep learning domain. We have SARIMA, that is a seasonal variant of the well-known ARIMA algorithm, whose definition is reported in the slides in the top left corner. This technique consists in three parts, namely the autoregressive part, controlled by the parameter P, the moving average part, controlled by Q, and the integrative part, controlled by the parameter D. ARIMA can then be extended to deal with seasonal patterns by introducing additional terms to this equation that are controlled by the seasonal counterparts of the three parameters that I just mentioned, plus an additional parameter that controls the seasonality period. Then we have alt winters, also known as triple exponential smoothing. Its peculiarity consists in explicitly separating predictive components into level, that is the LT, the trend, BT, and the seasonality, that is the ST in the formulas that you see. Alt winters can be used in its additive form, the one in the slide, or in its multiplicative form. For what concerns neural approaches, we have also nonlinear autoregressive networks, that are a kind of models whose forecast at time t is a nonlinear combination of the last k observation of the input signal. The one-needed layer sigmoidal neural network is a notable instance of this type of functions, and in this case, the parameters are usually optimized via backpropagation. Finally, we have LSTM, that is an improved version of the classical recurrent neural network. In particular, this variant employs a system of gates to address the so-called vanishing gradient problem. In fact, this network is very good at dealing with possibly long-term dependencies in long sequences. Besides the classical forecasting techniques in this work, we propose four different neural architectures, built on top of the neural approaches that I just mentioned. Such models are all examples of encoder-decoder architectures, that is a common architectural pattern for sequential data processing. An encoder-decoder architecture is composed of two distinct layers connected in series. The encoder, whose job is to accept a possibly variable length sequence in input and compute a state with fixed shape, and the decoder, that maps the state to an output sequence. Our baseline architecture consists of an LSTM layer followed by a fully connected layer, jointly trained by backpropagation. An input time series is fed to the LSTM that is set to output only the last value of its recurrent process for each internal unit. The resulting vector is then provided to the fully connected layer that outputs an estimation of the target time series in one shot. For this reason, the length of the output sequence is to be fixed up front, so that this architecture does not fully leverage on the recurrent nature of the LSTM. On the other hand, this model can also function in a multivariate mode. To work around the limitation of fixing the length of the output, we developed two additional architectures, whose inference process consists of using smaller forecasted sequences as inputs to the model. In this way, it is possible to forecast an unlimited number of time steps while using a model with a fixed output size. However, due to this closed-loop mechanism, such architectures can only work in a univariate mode, as they can process only the historical values of the target variable. The difference between the two architectures lies in the encoder. While the sec2-dense features an LSTM layer, the dense-to-dense employs another fully connected layer. As an attempt to get the best from both worlds, we developed yet another architecture that is capable of operating in multivariate mode while not being constrained in the length of the output. As we will see in few slides, the sec2sec is indeed the model that exhibited the best performance overall. The sec2sec models relies on circular time embedding to encode the contextual temporal information about the elements of the input sequences. For instance, the hour of the day of the week, whether the timestamp corresponds to an holiday, and so on. Thanks to the circular time embedding, we can encode time series of such values, respecting the periodic nature of the series. The time series produced by the time embedding, whose dynamics is known a priori, is then used as a pilot sequence for the sec2sec model. The equations on the left-hand side define the encoder E and the decoder D, that in this case are both LSTM layers, and also the rectifier R, a fully connected layer whose job is to merely reshape the result to the desired dimensions. The equations on the right-hand side describe how the input and the auxiliary sequences are combined to generate the output. The sec2sec architecture also leverages on an additive decomposition that takes into account the trend and the seasonality of the series. In particular, the equations in this slide account for the seasonal part of such a decomposition. A separate model is fitted on the raw data to capture the trend. Then the original data undergo the detrendization, and the encoder-decoder architecture is fitted on them. At inference time, the two models are used to generate the separate contributions that are summed up to get the final output. We focused our experimental evaluation on data coming from two distinct VNFs, namely the CSCF and the DRA. Both datasets report samples recorded with the hourly granularity, but we also resampled the DRA dataset to get a daily aggregated average version. The metrics under analysis was chosen by Vodafone due to their relevance in the monthly monitoring and reporting activities performed by the NFV capacity team. Both datasets span a time range of 16 months and reports the dynamics of the CPU usage average and infrastructure level metrics, together with other service level metrics that are KPIs indicating the specific service utilization. For our experiments, we reserved the last month worth of data for testing and split the remaining portion according to a 90-10 ratio to get training and validation sets respectively. We conducted our experiments on two different testbeds. In particular, we leveraged on Vodafone GCP environment to spin up a VM equipped with an NVIDIA Tesla V100 GPU that has been extremely useful to speed up the runs involving the neural architectures. Instead, for the classic and forecasting models that cannot be accelerated with GPUs, we used an on-premise server equipped with an AMD Ryzen 7 processor. Each model was tested under multiple different configurations of its parameters. If the training algorithm of the model involved random weights initialization, as it is the case for neural architectures, Each configuration was repeated for 10 independent runs to get a more fair measurements. Here you can see these tables that summarize the configurations that were tested. For instance, neural architecture were tuned according to the input length lambda, the output length phi, the number of units of the LSTM cell d, the batch size b, and whether the trend decomposition was activated. In this slide, we can see an overview of the results obtained by running the neural architectures over the CSCF hourly dataset. This dataset contains a stationary time series with a strong seasonality component. In these settings, sec-to-sec architecture outperforms the others in terms of accuracy. But the dense-to-dense has an interestingly reduced training time by an order of magnitude, at the cost of raising the error from 3% to just 4.2%. Also, we can see that sec-to-sec provides more stable results, as the 50% of the observation are densely concentrated around the average, and the whiskers of the box plot are relatively short. This entails that the model is very robust with respect to the hyperparameters variations. Here we can see the performance of the neural architectures when dealing with the hourly DRA dataset. Also in this case, the sequence-to-sequence architecture achieves the best performance, and we can see that in general its accuracy is more stable with respect to variation of the hyperparameters compared to the other models. It is interesting to note that for this dataset with a very huge forecasting range, the baseline architecture turns out to have a decoder that is a fully connected layer composed by 4,368 rows weight matrix. Given its size, we were expecting its training time to explode, which did not happen. This is probably due to the nice way the computation of the decoder can be parallelized on GPUs. Indeed, the other architectures do not fully exploit the GPU acceleration, either because they are made entirely of recurrent units or because of their closed-loop nature. However, defining the root cause of such an unexpected performance boost requires a deeper investigation. For the daily DRA dataset, we have the dense-to-dense model achieving the best performance overall. However, as we can see from the left-hand figure, the variability of the accuracies for this architecture strongly depends on the choice of the hyperparameters. For what concerns the classical forecasting techniques, results show that Alt-Winters outperforms Sarima, both in terms of accuracy and training time, for all the tested datasets. In particular, for the hourly datasets, Sarima generally requires more than 100 seconds per run, while Alt-Winters less than a second. In this slide, we have a few tables reporting the best performance observed for each of the tested models. Remarkably, we can see that Alt-Winters' best runs consistently scoring a slightly lower mean average percentage error than the sec-to-sec architecture, that is the best of the neural ones. However, such level of performance is most likely due to a particularly lucky shot in terms of hyperparameter tuning, rather than an evidence of its superior capacity at modeling complex time series. Indeed, the low stability shown by Alt-Winters seems to support this hypothesis. Without any other statistical assumption, for instance about the similarity of the distribution with other time series or different time ranges, these results suggest that Alt-Winters is less likely to achieve the same accuracy of the sec-to-sec architecture for the tested datasets. The figures on the left show that the hyperparameters choice has a strong impact on the performance of Alt-Winters. In fact, for all datasets, the worst Alt Winters runs score a MAPE that is very close to 100. This is not the case for sec2sec, whose overall worst performance is around 10%, as we can see in the figures on the right. On hourly datasets, despite the best Alt-Winters run achieve a MAPI lower than 3%, the first quartile is greater than 5%. Instead, for sec2sec, the third quartile is lower than 4%. In other words, 70% of Alt-Winter runs score a MAPI greater than 5%, while 70% of sec2sec runs score a MAPI lower than 4%. Similarly, on the daily DRA dataset, despite the best Alt-Winters run achieves a MAPI lower than 2%, the first quartile is greater than 3%. In this case, the sec2sec architecture exhibits a third quartile strictly lower than 3%. In other words, 70% of the Alt-Winter runs score a MAPI greater than 3%, while 70% of sec2sec runs score a MAPI lower than 3%. In conclusion, deep learning techniques and the sec2sec architecture in particular exhibited comparable performance with respect to classical forecasting techniques. However, neural architectures appear very much more stable than the others, that are quite susceptible to hyperparameter variations. In the future, we aim at extending this work by running our models over more data extracted from Vodafone RFV data centers. This way, we can keep on providing the operation teams with effective tools that can deal with the highly variable scenarios that are typical of large-scale cloud environments. In addition, we would like to improve our model by exploring other techniques that would bring us to benefiting from additional information that are usually available in operation context. For instance, we could integrate feedbacks from domain experts or information regarding the topologies of the specific VNF deployments. This concludes my presentation. If you are interested in knowing more about our work, feel free to drop me an email or connect with me on LinkedIn. Thanks for watching.